All right. So welcome, everyone. Thank you so much for joining today's CSML seminar talk, which is kindly sponsored by DeepMind and Alice. We have the great pleasure of having Marta Garnelo here, who is the leading person behind a new family of neural models, neural processes, which received a lot of attention recently. Marta is a senior research scientist at DeepMind, where she has primarily worked on deep generative models and meta-learning, and was involved in developing generative query networks. Prior to her work at DeepMind, she obtained her PhD from Imperial College London and is a co-author of many popular papers, such as Reconciling Deep Learning with Symbolic Artificial Intelligence, Neural Scene Representation and Rendering, Deep Unsupervised Clustering with Gaussian Mixture Variational Autoencoders, and many more. Today, she will talk about her recent line of research on meta-learning and neural processes, and I'm really excited about today's talk. And without further ado, please welcome Marta.
Yay. Hello, everyone. Thanks a lot, John. As John said, my name is Marta. And I'm actually particularly excited to be talking about CSML today, because this used to be a seminar series that I used to go to when I was a master's student and a PhD at Imperial. And I used to take the underground and go all the way to UCL to watch these talks. And it's nice to be on the other side of the room now, even if it's virtually. So as Jean mentioned, I've primarily worked on deep generative models at DeepMind in my past 4 years. Although I have been doing a bit of multi-agent and game theory recently, but the work that I want to talk about today is on neural processes, which falls on the category of generative models. Before we start, I normally, if anyone has been to any of my talks, I like them to be as interactive as you guys want it to be. So if there are any questions, I'd encourage you to ask them throughout the presentation. Especially if something's not clear, then that usually means I'm not doing a good job at explaining. So please, please, please ask. I'd like everyone to get an overall understanding of what's going on. And I tend to keep my talks fairly high level as well. So yeah, good. I think with that out of the way, yes, I never use Zoom, but I think you are allowed to unmute yourselves and ask questions if I understood Jean correctly. So please feel free. Cool. So this talk, as I mentioned, is about neural processes. And there is many angles from which you can explain or think about neural processes. As I mentioned, it is a deep generative model. It's also a regression algorithm, or you can think about it from a Bayesian perspective. But one of the aspects that I want to consider today is to look at it through the lens of meta-learning. And in order to do so, I am going to use this opportunity to first talk a little bit about meta-learning, maybe give a little overview over these different models, and then maybe put neural processes into context and talk a little bit about those. Cool. So with that out of the gate, let me see if I know how to pass the slides. Yes, good. Meta-learning. So what does meta-learning mean? I'm sure most of you have heard about it. You know, it's often referred to as learning to learn. But let me give you one small example. So imagine you have this maze over here, where you have these objects that an agent can collect, and depending on their color and shape, they're going to give you a different reward. So the red ones could give you a really high reward, and the yellow ones, for example, really low. So traditionally in machine learning, you would train an agent that learns this mapping, like red is good, yellow is bad, and just learns how to act in this world. And that's all it essentially learns. With meta-learning, we have asked a bit of a different question. In meta-learning, every episode, the reward that these objects are going to give you is going to change. So maybe in one episode, red is really good, but then in the next one, red is actually the worst one you can get, right? So what you would like to do is you would like to your agent to have a bit of contact with the world, and then at test time, still be able to integrate some new information, right? And that's why it's called to learn, because you still want your agent to be able to integrate this information at a test time or inference time, like we call it. So what does this mean a bit more formally in terms of learning, training, and data sets? Let's look at the problem of image classification, which is a very standard supervised learning task in machine learning. On the left-hand side, we have traditional image recognition. We're going to have two classes, which are cats and dogs. And these images, the images of cats and dogs are going to have labels. So dogs are going to, quick question, can you see my pointer? That might be, is this visible? Cool. Okay, so dogs are always, in case you don't know what a dog is. So dogs are always going to have the label 1 in this case, and all the images of cats are going to have the label 2. And that's going to be the mapping that you want your neural network, if you're using one, to learn. On the left side, this looks a bit different. This is what we use in meta-learning. And what happens here is that similar to before, where every episode the reward could change, what we're going to do is at every episode, the labels are going to change. So unlike before, we would start an episode by selecting either all classes or a subset, and then assigning them a random set of labels that are consistent for each of the classes. So every element that looks a bit like this would be a 2, for example. But then across episodes, the labels would therefore change. So this one here, who was a 2 before, is now a 4. Of course, it would be crazy to expect our models to be able to just guess random labels. So what happens is that at test time, we're going to give our agents some observation, some like solved tasks. So we're going to say here some images with the labels, and then we want it to learn from that. So given that we have this, what is the class of this one over here, right? Yes, and then essentially this is what is the big difference in terms of data sets. In traditional machine learning, you're going to have one big data set of X and Y pairs. Normally, there are fewer classes, but there's many, many examples per class. Think of ImageNet, for example. On the other hand, in meta-learning, you're going to have, again, this set of X-Y pairs, but it's a set of sets, right? You can consider that this is one set, and then this is going to be another set. So you have this like set of smaller sets. What this often means is that you're going to have loads of different classes, but you don't need that many examples per class because it's not about that particular transformation between that image and that label, right? You just want to learn something that can quickly adapt to what it's seeing. And we're going to refer to it throughout this talk. The little bits of information that I'm showing at test time for you to then be able to make the inference is the context. So those are the examples that are given of the solved problem. And then whatever you're trying to predict, that's going to be the target. So just for nomenclature. And cool, yeah. So I'm sure some of you have encountered these data sets that are very common for meta-learning. So a very famous one is this Omniglot data set from Brendan Lake, which essentially is a lot of symbols from different characters. And again, as I mentioned earlier, there's loads of different classes because there's many different symbols, but there's only actually 20 examples per symbol. So you want something that if you give it the answer, it very quickly learns to match what are other symbols that look similar. There's also Mini-ImageNet, which is like a reduced version of ImageNet that is specifically done for this type of meta-learning task. And then there is regression. So neural processes, even though I've been talking about classification the entire time, neural processes are primarily used for regression. But if you think about it, classification can be thought of or in the context of regression as well. So you can look at traditionally, you are learning this, albeit not continuous function that maps from image space to label space, and it's this fixed function that stays like this throughout training. Whereas in meta-learning, you're going to have this function that maps from image space to class labels, and this function is going to vary depending on how you set the labels for each of the episodes. So all you're doing here, again, is you can see this almost as a regression problem. Of course, normally, instead of regressing these type of step functions, we're more interested in regressing continuous functions. So I'm showing this here just to make it maybe, again, a bit more clear how it works in regression. So in traditional setups, we would have this one underlying function. Imagine, for example, a Q function. And what you get is different batches from that one function, and you're trying to approximate that one function as good as possible. Whereas in meta-learning, what you get is that every episode, you're going to get one function and some observation from that function. So again, it's this notion of having data sets over data sets.
Sorry to interrupt you, just because you said you want to have it more interactive. Someone just asked something in the chat. So can we consider meta-learning as inductive bias learning?
Maybe, yeah, yes. Okay, so two ways of thinking about that. I could see how that could be the case in the way Chelsea Finn frames it, and I'll talk to it a bit more, where you're trying to find some representation that gets you the fastest possible then to classify, and this will make more sense in a few slides. More than inductive bias, I'd almost say it's like you're trying to learn the kernel of a GP. So you are learning, you're using your data to learn some sort of structure, but I don't know if I would call it a bias. You could probably see through the lens as well. I mean, in general, this is always what we're doing, but I'm trying to see how I can phrase it through this particular framing. Okay, let me come to you back to it in a minute, and then we'll see. Meta-learning, few-shot learning, very good question. It's essentially the same, yeah. Or let's put it this way, all of the meta-learning experiments are few-shot learning. I mean, few-shot learning It can mean many things, few shot, but in this particular case, it's exactly this. You wanna have a test time with as few examples as possible, be able to predict the right answer. And this, because it's few shot, this shot implies that you are getting some context points at test time, right? Otherwise, this shot wouldn't mean anything. Does that answer make sense? Also, guys, totally feel free to speak up and also tell me if what I'm telling you does not make any sense. Yay, cool. Sweet. Yes, okay. So let me formalize this a little bit, and maybe we can also talk about some of these questions. Good. So as many of you will know, this is I'm just writing out the supervised learning objective. More formally, we're usually call these images X. Those are our inputs, and Y's are our targets. Those are the labels. And essentially, all that we're doing in machine learning is we're trying to get a model that gives us this conditional probability, right? We're giving an image. We want the label. And this model is going to be parameterized. Often we use a neural network for it, for example, but it doesn't have to be. And the way we find these parameters is by optimization. We want the optimal parameters, that's this here, by just taking the expectation over the entire batch, right? And Y and X are going to be sampled from our batch. Now, when we think about meta learning, I've highlighted the differences a little bit. We're going to, again, have pairs of X's and Y's, but we're also going to have this distinction of C and target. Basically, what our model is modeling is what's the probability of Y in the target and X in the target given our context, right? So all of this that we've added. And in addition, what's also important is we're not only taking the expectation over the batch, but we're also taking the expectation over all of these different distributions. Like I said, we have a distribution over data sets rather than a single one, right? And you want to find the optimal parameters for that. So if we look at this equation, basically, again, this part over here, this objective is essentially shared across all of the models. The way the models differ is essentially in how you approximate this probability over here. And essentially, this is what I'm going to use to break up the different areas I think that there are in machine learning and maybe give you a little bit of an intuition. So there's three main ways that you can approximate this, this probability. Or common ways. The first one is metric-based, then we have gradient-based methods, and then finally we have model-based, which is what neural processes do. So the metric-based is actually also very simple. So you're saying, okay, the probability of this Y is going to be, it's very similar to kernel methods. It's going to be some distance that I parameterize between the X's of my context, so everything I've seen, and the X of the target that I'm interested in, and we multiply it. We take that distance and we use that to multiply it with the context observations. Okay, what does this mean in a nicer example over here? Imagine you have these pictures of the dogs. So essentially, this kernel here is just calculating the difference, like how similar are these images of dogs? So probably this one and this one, because they're both German Shepherds, they would get very high weight, whereas all of these would maybe get lower weights. And then we're multiplying those weights with the labels of these dogs, right? So because these two have a very high weight, then it would essentially say, okay, you can see here, very high weight on red, and it gives us red. So essentially what this is called matching networks. And essentially what it's learning is how to compare images at test time. How to best, once you test them, you're given some context, how do you best compare it with a specified kernel? And this is kind of the important bit, that the kernel is pre-specified, and it can be any metric that you want to compare your images or whatever inputs you have. There's been lots of follow-up on these metric-based ones. We have Siamese networks. There's also Snell public. Oh God, I forgot the name of this particular model. But essentially, what they do here is that rather than comparing to all the images, they compare to these centers. So they get like the mean of the clusters for those different context points, if that makes sense, across the labels. Cool. So that is the metric-based. Another way of doing it is so-called gradient-based meta learning models. And this is MAML is probably the most famous on this one by Chelsea Finn. And essentially, what we're going to say is, okay, this probability is going to be a function of the targets that we want to predict and the context. But the parameters themselves of this function are also going to be a function of the context. What does that mean? That our neural networks, the weights themselves are going to depend on the context. And the way this is done is that even once it's trained, you get your context and you still do a few gradient updates to then get the separation into the different classes. And so essentially what you are trying to do is you're trying to find to try to have a model that finds the best possible position in space, such that with minimal amounts of then gradient steps at test time, you can very clearly differentiate between the different classes. I hope that that makes sense. And in a way, that could be seen as a bias in my head. I'm happy also to be proven wrong. And MAML has been applied to a lot of things, originally also on image classification, but also a lot in reinforcement learning. So there's a lot of cool stuff that Chelsea also has done, and others on applying this to robotics and NRL. And finally, model-based meta-learning models is, again, we're going to say this probability is going to be a function of our target X and the context, but we're just parameterizing it. We're amortizing everything, and we're just saying we don't specify any particular distance or any kernel like the metric metric-based we're doing, but we're also not going to have any gradient updates at test time. So at test time, this is just going to be a function of our inputs, and then that's it. We don't update our parameters. And neural processes, as I will talk to you about in a second, is exactly part of this. Cool. Just as a recap about the data set that we're going to be looking at for these examples, and just to remember, it's not going to be a single function, but rather we have this distribution over distributions. And this is quite crucial in training neural processes, because then at test time, the neural process doesn't know what to expect and actually expect some context observations before it can make any predictions. I'm not sure. Prototypical nervous. Yes, thank you, everyone. Also, I have you guys on this screen, so someone please shout if you need me to look. Wow, you guys are on top of things. Thanks, Kai. Kai's a friend. Cool. Is this clear so far on meta learning? Any questions? Sweet. Cool. Oh, good. So I'm going to talk about neural processes first and how they relate to all of this. And in order to do so, let me show you a little animation on how they work. So essentially, as I mentioned, we're going to have this task where we have some unknown function, that's the blue line, and we're going to get some observations, X and Y, some pairs along this curve. So the blue line is unknown to us, but we have observed those red points, and we have the X and Y pairs. In addition to that, we're also going to have some target points on the X-axis that we want to predict on the Y-axis, right? So that's our XT over there. So what we're going to do is we're going to pass all of these pairs through an encoder that is shared to generate these individual representations R1 to R3 in this case. And then we're going to aggregate them. And we want to aggregate them in a order invariant fashion. So usually we just either sum them up or take the mean. And we get this global representation R. So now R is meant to contain all of the information about that blue curve that we have obtained from these few observations pairs. We then combine this representation with our target X and pass it through a decoder. And this decoder is going to output the mean and a variance of our probability distribution. You can see it also here. We have a mean and some variance over this. And the way we're going to train this is we're going to use this mean and the variance to parameterize, and well, in the case of a Gaussian anyway, we're going to calculate the log probability, so the probability of the actual Y value that we have from training for the target, and calculate the probability under our predicted distribution, and then we're going to use that to backpropagate. The good thing about this particular setup is that once we have calculated R, we can actually sample loads of X's in parallel. So you could imagine sampling here and here, and we can all pass them in at once, right? Through through parallel decoders, essentially. And so the way this would be trained is you get your function, you get some of the points of that function as your observations, the red ones as your targets. You pass the context observations and encode them and predict at the targets, calculate the probability of the actual target values in this particular example. And then most importantly, in the next training round, you discard that function or you put it aside, pick a different function, pick a different subset of observations for context and for targets, and so on. And you do this repeatedly every time you have a look at a different function. And this is what a neural process looks like on 1D regression once it's successfully trained. For those of you that have done GPs, this looks like a bit of a less pretty version of what Gaussian processes do. What we see here is in black, that's the ground truth function that we're trying to predict. And in blue, that's the predictions of the models. And we're showing the model increasing numbers of observations. Those are the black dots. And the model changes, obviously, its predictions, the more observations it sees. But what we can also see is that the variance, which is in light blue, is also originally very big, and it remains large in those places where it's not seen any observations, but then gets smaller as it has more certainty as to what the underlying function looks like. Also, maybe as an intuition, the reason that this learns the variance so well is because the model learns that if it's very certain, if it's certain about its prediction because there's an observation nearby, or because from the implicit kernel that it's learned that another point is giving him some information about its current prediction, it's worth for the model to learn to put small variance on that because it will get a higher reward. Whereas if it's very uncertain, it learns to actually spread out the variance because then it will still get some reward signal at least, right? As opposed to just better than none at all, essentially. So it does learn to estimate the variance in that sense. How would I deal with noise observation? Noisy in X, Y, both? Mark, hi, yay. How would I deal with noisy observation? So we did do noisy in Y, which is why that black line is not perfect, and that seemed fine. Noisy in X, we've not really tried out, and I think that would also probably be a bigger issue. Yeah, probably overfitting. Definitely with a simple model, I think you would run into issues. Yeah, good question. What are the usual aggregation methods? So we, for our initial paper, we literally just either took the mean or added up across all of these R's. And that was actually enough, that we didn't lose enough information, but also obviously the tasks were quite simple. There's a bit of a trade-off because if you know that there's some underlying structure, you can actually make it a bit more complex. I know there's been work of using graph nets, and there's also been work on doing this sequentially. So using, for example, LSTMs or whatnot to aggregate. But in doing so, you are removing this order invariance. So you are putting on some structure that is totally fair enough, but just be aware that that's what you are doing in that particular case. If that answers the question. The relation between what? Yeah, it's going to. Yes, absolutely. And that good question. Thank you, Mahalingam. I hope I didn't butcher that one. So one of the things that we found interesting is because obviously if you have these type of functions which are beautifully generated from GPs, you should use a GP because that's what they're good for, and they're going to do a better job than this. However, sometimes it might be the case that you don't know how to express something with a GP kernel. So you could hope that maybe a neural process could learn the kernel, if that makes sense, from the data. One example for this, for example, is I came up with this experiment thinking it would be really easy to get across, and I've been at conferences struggling a little bit, so hear me out. We're going to take an image, okay, and look at it flat, and that's going to be the position of the pixels are going to be our X values, okay, so it's the two-dimensional X values, and then the RGB color at each of these pixels are going to be the Y values, so we have three-dimensional Ys, okay, so from R2 to R3. And then given some of the pixels, so we say at this position, this is going to have this color, at this position, this, and so on. What is the color at a certain other pixel position, right? So you can imagine that you're regressing this very funky looking function that doesn't necessarily, that is not continuous and it does not fit into any polynomial or exponent relation or anything like that. It follows the structure of faces, if that's kind of what it's capturing. Yes, and what we did for those experiments is essentially we gave it either one. So here what you can see, the black image is, if it's black, it's unseen points. And the colors are those context points that we've shown it. So here we've shown it 1 point, here we've shown it 10 points, 100, and here almost all of them, so 1,000. And then here we're asking it to predict all of the other pixel points given that. So it's creating an image. It looks like image generation, but really it's still doing this weird regression essentially. And we can see that it does a pretty good job at, like, obviously this is a tiny model and it's not perfect compared to GANs or what we can achieve today. But already from 1 pixel, so it learns the skin color, it does a pretty good job at predicting almost the kernel of a face. It learned to capture both the mean in this case, but also learned about the variance. So it's learned from the data set that obviously the backgrounds, given the face color, the backgrounds are going to be very varied. There's going to be loads of uncertainty about the shape face, but not that much in the middle of the face, basically. And then as you increase the number of context points, your mean goes from being a blur to a beautiful woman and then to a man, because CLP is somewhat biased towards obviously beautiful women because they're celebrities. As you can see, also the variance is correctly reduced. So you have originally a lot going on, and then as you see more of the background, it actually, sorry guys, I think that's kind of covering, so I stopped moving. It actually just stays around the edges of the face. And it's still not perfect if you look at the reconstruction, even though it has the observations. And this is something that we'll talk about a little bit more later. The reconstruction, the mean is still by no means perfect. So this gives you a little bit of a trade-off. So we compared this to other more kernel methods. So we have k-nearest neighbors and GPs. And of course, GPs, if they observe the entire images, do a much better job at reconstructing than we do, because this is the mean that we have, and this is not very good. But in the low context regime, using a GP with a Gaussian kernel is obviously not going to do a very good job at this, because it is a Gaussian kernel and it's not going to express exactly this. So this maybe shows you a little bit that there is this trade-off. If you know how to express something with a kernel really well, or you're in low dimensions, then using a GP definitely makes sense. So you're going to get not only guarantees, but good uncertainty estimates and so on. If, however, you have loads of high dimensions and maybe your kernel is not as straightforward, then you can maybe try to learn it from the data using this type of neural network. Hold on, there is a question. Locally weighted regression here as KNN suffers. What do you mean by that? Can you, Gabrielle, hi. Can you explain to me what do you mean by locally weighted regression here as KNN suffers from boundary bias? Also, honestly, guys, feel free to speak also. If you can. Okay, I'm gonna go on and then we'll come back to this one, okay? If that's okay. Cool. So finally, just this is all the initial conditional neural processes paper. We also showed that this can be phrased as a classification problem. Much like I showed you earlier, you can think of classification of this step function regression. And essentially what we did here is we tried out omniglot, where the images, the X's were entire images, and then the classes were the labels. One of the things that we found that we had to do here is that actually when we aggregated the classes, we couldn't just aggregate all together. We had to aggregate across classes. So we aggregated all of the class A, all of the class B, all of the class C, and so on, and then concatenate them. Because if we did everything together, the model wasn't able to learn. And this is actually something that other people have also observed. So that's like a little tip on the side, which you're allowed to do because you are given the labels of the context. And then what it outputs is some logits over what it thinks the correct label is for that one. And what's also interesting is that whenever it sees it is presented with an image that is not in the context, like this one here, it actually often gives you good uncertainty estimates. So its predictions are a bit more uncertain than you would if it's actually observed it. And we get good results. Like it wasn't like anything insane, but given that we were basically using 2 MLPs, it was very good. And the runtime was faster because it was not I was pointing at the screen with my finger, which I don't think helps. It was not n times m, but rather just additive because of this summation in the middle. Good. Haha. Sorry, thank you, Joao. N and M are the number of context points and the number of target points. So normally, if you're comparing all to all, you would have this big matrix that is n times m. That's why the runtimes is that. Whereas in the other one, because you're doing n and then aggregating and then comparing to m, it's just this addition rather than multiplication. I hope that answers that. For the classification one. So for this one, Lawrence asked what neural network architecture did I use? Yes. So for this one, the encoder was a ConvNet because we were dealing with image input. So we would encode the images with a ConvNet, then attach the label, and then pass all of that through an MLP. And that would essentially be our representations. And then for the decoder, just a normal MLP. sorry, and I should say, obviously, the targets, again, everything that had an image as input had to first be passed through a convnet, but it wasn't particularly extraordinarily like complicated or anything. If that makes sense.
Thanks, Marta. That's really interesting. Yeah, just wondered if you tried any other sorts of architectures for different problems and what you think might be appropriate in different contexts.
Mm-hmm. So for these small scale problems, MLPs were more than enough because half the time we were doing actually something quite simple. There's been follow-up work, and I'll talk about it in a minute as well. There's been someone adding attention. There's also been some for we've had RL and we've also had Bayesian optimization, and where essentially we just had bigger networks. We've not done anything incredibly insane. I know there's been work also with using graph nets, so that might be worth if you're interested in looking at different ones. But beyond really adding attention, there's not been a lot in terms of architectures, mostly because the problem didn't require it. So I suppose if you had a problem that is very hard, then you could try to do little tricks and pieces here and there. Here we also added residual connections, by the way, I don't know, both in the encoder and the decoder, as a little detail. But yeah, nothing insane from our side, at least, was tried.
Thanks. Just for thinking about kernels, they tend to assume the underlying function is kind of smooth, like sort of kernels you use in Gaussian processes. But do you think some of these other architectures that you've looked at would work for sort of non-smooth functions, or that are kind of a bit less smooth, so they're more sort of powerful for that reason?
Yeah, so ideally you would like it to learn these non-smooth functions. I know that there are GPs that there's lots of GPs, and there's a lot of work also on deep GP. So I'm no expert on any of that by any means. So they're not as restricted to smooth to completely like this typical Gaussian function that you would expect. But yes, definitely a neural network, while it has fewer guarantees, it at least often is more flexible in what it can actually model. Yes, rather than like a kernel, often you have to like sit down and write it down, and it might be harder to express just exactly what you want in a closed form solution, right? Yeah.
Thanks.
Thank you. Gabrielle, is it okay if I wait for the question since it's longer for the end of the talk and then come back to it? I'm not completely ignoring you. I'll do that if that's okay. Cool. Cool. So far, I have been talking about this model that we called conditional neural processes, which essentially was, as I showed you earlier, is this model over here, which was completely deterministic, right? So if I gave you this image of this lady and gave you some context points, what I was showing you so far was always the mean prediction, right? But if I asked you to give me different possibilities or different samples that match that context, the only place where you can really sample would be from this, because that's the only distribution we have. But because these distributions are all generated independently, so they're just Gaussians for each of the individual pixels, if you were to sample all of them, what you would get is essentially some noise on top of this mean prediction, right? And what you would like, rather than this funky lunky picture, is different alternative faces where all the pixels are coherent. So there were a few ideas that we had for how this could be done. You could try to learn so at the moment you can think of the predictions of all the pixels as having just one multivariate Gaussian with a diagonal variance. So instead of that, to learn the covariance, right? So that would give you essentially when you sample from that, it's like sampling from a GP, then all of it would be coherent. Although it can be a bit hard to learn covariances with neural networks. Another option could have been to do the pixel generation autoregressively, so sample the first pixel, and then based on that, loop through the entire model until we've sampled all the pixels. But by doing so, we were losing part of what we thought was a good selling point, which is that you can generate all of these pixels or all of these predictions in parallel, right? Because it has to be done sequentially. So instead, we went for the third option, which was to introduce some stochasticity and latent space. So turn this representation that you can see here. Instead of having R, what we're going to do is that our representation is going to encode some latent distribution, in this case a Gaussian with some mean and some variance, and we're going to sample a latent variable from our from the space, and then we're going to condition all of our targets on the same Z. So what I'm showing you here is exactly this. Those are different samples of Z. I'm still showing you the mu, so I'm still only showing you the mean, because again, if we sampled from this here, we would have this noise. So I'm still showing you the mean predictions, but because we can sample these different z's, we can actually generate entirely different faces that match this context. And this is what we then call neural processes without the conditional in front of it, which was a follow-up paper. And a bit confusing, I think. So just to reiterate, what conditional processes can do, they can predict the mean function, as you can see here, for the curves, as well as the variance at each of the points, but we're not able to generate entire samples that go through that, that are consistent with this trajectory, whereas with neural processes, we now can. We can actually sample entire trajectories that are consistent with the observations and are consistent across samples. And this is very useful. I mean, you might wonder why one want to do that, but there are several applications of this. So one of them, for example, was to use it for black box optimization, where you essentially what you do here is you have this underlying dotted line that you want to minimize. So you want to find this point here. And what you have is a model of this function, because you only have access to some samples of this function, and it's very costly to evaluate. So you want to have to evaluate it as few times as possible. So you observe at this point, and then you update your model, which is the blue function, and say, okay, that's what I think the model is. And then you search for the min of that function and say, okay, this is the next one that I want to have a look at. And then you observe that in your from the ground truth, which again is expensive and you don't want to do many times, and then repeat and so on and so on. And for this, you have to be able to sample and try trajectories in order to carry it out. So this now we could do with neural processes. And we use this, I'm not going to get super much into detail because of time, but we did this contextual bandit experiment that has been done previously as well with a number of other meta-learning problems, where you have to, based on some observations of these different colored areas, you have to choose which of the bandit levers to pull, and there's going to be different sets of circles. So again, it's a set over data set, so you're going to have different situations where the radius of this blue one is larger or smaller, and we do pretty well. So that turned out pretty nice, and it was nice to see that this also worked with something like neural processes. We also use this for later work by Alex and Jonathan, also from DeepMind. Use this for black box optimization for recommender systems. So this was a much bigger problem where you say, okay, I see some observations of people's reviews, and then how can I choose what to recommend next? And another interesting project that in that same paper, if you're interested in different applications that can be done with neural processes, was this of finding the worst case position for a search task for an agent. So what this means is you have a maze and you have an agent, which is this little star here, and you're saying, where can I put the goal such that it performs the worst? Right. And you can either, I guess you can either change the goal, you can change where the agent starts, or you can even change the layout of the maze. And the motivation for this is to find the weaknesses of an agent and then hopefully be able to train in a curricular fashion, train it in its blind spots, essentially. And neural processes did a pretty good job actually at predicting how an agent would do depending on its start position by seeing how well it would do getting to specific endpoints, right? So what this is saying is a heat map where if the agent starts here, how well would it do depending if this was the end or this, or for each of the pixels if that was the particular endpoint. This actually happened to be an agent that was very biased towards going to this site. So it actually did pretty poorly when the goal was quite close to him, even though it was very close. Yeah, so you can see that already with seeing just 3 points of how the agent does in this maze, it actually did an okay job at estimating this landscape, which is really actually quite exciting, because then it can interact with different agents and see, okay, if I see this agent interact in the maze a little bit, can I then estimate what its like flaws are going to be, or how to, yeah, where it's going to fail. Another interesting project that I started originally with the first neural process paper, but then it only ever came out in this last one, was to use it for model-based reinforcement learning. And this was very inspired by Pilko, actually, which Mark is here, so that's exciting. And essentially, what you're in model-based reinforcement learning, you are essentially, when you have an agent that is interacting with the experiment, with the environment and collecting experience, you can include a model such that the agent can actually get a lot of that experience from a model that it has internally, and it doesn't have to actually have the experience in the real world. So this was very useful. For example, if you're trying to do robotics, then you don't need to have the robot do all of the exploration in real life. You can have the model, the robot can have a model of the world, do rollouts in his head, and then update the policy based on that. And what we did is we integrated, we use a neural process for the modeling bit. So what this essentially meant is we wanted it to be a meta-learning distribution. So we had our task distribution were different card poles with different pole masses and card masses. So at every episode, the agent wouldn't know what type of pole it's dealing with. And it had to, from as few interactions as possible, figure out which one it is dealing with and actually then carry out the policy as best as possible. So what the what the inputs were is that our X were essentially given a state and an action. Imagine that the regression, given a state and an action, you are regressing what is going to be the next state, and that's a model. So you can almost model the dynamic of any pendulum with that model, and you would want, with as few observations of that pendulum as possible, to model that particular one well, and with its particular mass of the pole and of the card. And so we trained neural processes on this, and we saw that it did a pretty good job at predicting both everything, like across like card position, pole angle, the velocity, and whatnot. So what you can see here are different rollouts, so of the actual environment, and then that's the model, the rollouts in the little dashed lines. So it does a pretty good job at the very least approximating the model. And let's see if this plays. Good. And we were able, of course, to do to learn very fast, because we are learning from this like simulated experience. Essentially, with only a handful of observed episodes, it was already able to have a pretty good approximation of what the card pole dynamics was, and then be able to learn from that. Cool. So those were some applications. Finally, I wanted to mention another line of research that was also done at DeepMind, which has to do with the fact that the reconstructions, as I showed you, were not very good even at those points that it had observed. And one solution that was proposed by Hyunjik later on was to add attention to both the encoding of the individual representations, but also attention of the context to the target positions. And by doing so, yes, what we get here is, as I showed you earlier, sometimes even if you have the whole context, the model might not do a fantastic job at reconstruction, so it gets the general just right, but it's not pixel perfect, which it shouldn't do, right, because it has the ground truth. And then now if you add attention, it's actually able to make sure that if it has the information, it really reconstructs those pixels well. And you can also see this in regression. So the line goes perfectly through all the pixels, while here it was more trying to do some mean that kind of came the closest to as many as possible, essentially. What was also interesting actually about this line of work is that looking at the different attention heads. So we have different types of attention, and the code is also online. This particular one is different multi-head attention. And then to look at, if you're looking at this particular pixel over here, where is that pixel attending to? And the different colors are the different heads. So you can see that some heads are just looking at the same column, some are looking below and above. But interestingly, it's learned from faces that there is a certain symmetry. So one of the heads is looking at the other side. So maybe like understanding the ear symmetry. And there's one that's looking at the top. Maybe you could argue that it's looking at hair color or something along those lines. So it was interesting to look at some of these attentions and think about what the model is doing on the side. And this allowed us to do pretty cool experiments as well that were quite high resolution. So Hyunjik had some experiments where he was literally taking these 4x4 images and then generating these are the context points, and then asking it what the pixels in between those would look like, and just generate faces from this, which I thought looked really cool. Cool. There's been a lot of follow-up work, and actually I have a long to-do. It's not even mentioned here. I have a long to-read list of related models. Also, even recently, also at NeurIPS, there's been some cool papers. So this is by no means the whole list. I'll finish with a little summary of how I like to think about neural processes in the context of regression algorithms. So when I think about regression algorithms, there is two main ones. There is neural networks. Neural networks have parameters. They're usually initialized somewhat randomly. And then during training, they observe loads of data points, and then they try to optimize the parameters such that they can predict these data points correctly. And the hope is that then at inference time, when we see data points that we haven't seen yet, that the parameters we have learned do a good job at predicting at those ones as well. What is really good about neural networks, and I think why people like them, is that you learn how to optimize these parameters from the data directly. Because there's so many parameters, you can model very complex functions. And the evaluation at test time is super fast, because all you have to do is a forward pass, which is matrix multiplication, which we're really good at. On the other hand, of course, there's Gaussian processes for regression. If we ignore the choice of kernel, which is a separate maybe can of worms, usually there's no such concept of training. So by choosing the kernel, you have some prior belief over what you believe the distribution over your functions is. That's this one here. And then at test time, you would get some observations, very similar to like meta learning. And you update your belief about what the underlying function is based on these observations. What I really like about GPs is that they learn this whole distribution over functions rather than the single one. So this lets them be very flexible at test time. And that they do have this measure of uncertainty. So given this test observations, they still have this uncertainty measure. With neural processes, we try to get some of the characteristics of both. They are learned from data directly. They can model. They're initialized at random, much like neural networks, but instead of initializing a single function, we're initializing a distribution over functions. And after training, we hope that from the data, it's learned how to reflect this distribution, and then such that then at inference time, if we show it some examples, it can actually narrow it down to those two. Of course, this comes at the cost of needing this dataset over datasets training regime, which is not always available. Of course, also more compute, and it doesn't come with the guarantees that you would have, for example, for a GP. At the same time, it does learn the function approximation from data directly and can model fairly complex functions like images of faces. It's very fast to evaluate at test time because you can just do a forward pass. You are learning this whole distribution over functions, and you have some measure of uncertainty, which reflects, at the very least, reflects the uncertainty present in your data set. So that's all that you can say about that. And with that, if you are interested in the code, we have code for conditional neural processes, and also the attentive ones. They're on the DeepMind GitHub webpage, and it's in like these little collaboratories that have explanations, and you can run them straight away and just see how it works. Also, as of end of last year, I got Twitter, so I can now finally be a cool person and say like and subscribe and all of this. So obviously, I actually don't post much at all. So, but there is that. And yeah, those are some links of interest. I don't know if these slides will be online. Yeah, and it always takes a village to do research. So I would really like to thank all of these amazing people, and probably many more that were behind all of this, and that made this actually a quite exciting journey. Yay, thanks.